Hope you're all doing well. Before we start, just a very short announcement. So next Thursday at 4 o'clock in the afternoon, we have, I should say, some kind of a blast of a webinar prepared for you. We will have Bertrand Maillot from GEC in Paris visiting and talking about their use of limit analysis in tectonic studies. And now this is what these guys are doing is something completely different from, well, let's say standard, your standard slope of foundation. And Bertrand and his team, they do these amazing studies on both very small scale laboratory tests with sandbox up to large scale simulations in several 100-kilometer domains. And the main motivation for the group's work is, well, there are several things they're doing. There are looking at exploration of hydrocarbon resources. They work with the French company Total, which is also a trusted Optum user. And they also look at different applications such as hazard mitigation. So next Thursday at 4 o'clock in the afternoon, Bertrand is coming by and he'll be talking about this. So be sure to sign up for this on our webpage, and I'll also send out a link afterwards. So then we have today's webinar. And this is something that is going to be extremely interesting. So as always, we have interesting topics, but this is one of the, let's say, one of the most fundamental parts of geotechnical engineering. It's really back to first principles, and I think even maybe you can call it the mother lode, or the place where everything starts, and maybe also the place where a lot of geotechnical careers sadly end. So this is, of course, I'm talking of course about the bearing capacity equations, or equation, which Kristian is here to talk about today. So as always, Q&A at the bottom, and recording will be sent around afterwards. So please, Kristian, the table is yours.
Yes, thanks, Sean. And I think we'll do Q&A, of course, as usual, but I think we might, if any of you are interested in being unmuted, you can raise your hand and then I'll unmute you. Everyone is muted by default, but if you're interested in participating like that, then please raise your hand. At the end of the webinar, I think is better. I can already see some raised hands now, so I think we'll take questions at the end if you don't mind. So let me share my screen. And the motivation for this webinar was a very frequent question, probably the most frequently asked question we get, and that is, why don't I get the same result with Optum as with the bearing capacity equation? So when people start using the software, they typically, and that's what I would do myself, try to reproduce some of the classic solutions, your 2 plus pi, and then you sort of move up from there, and then at some stage you're going to find some disagreement between the bearing capacity equation and Optum. So so that was the motivation today, to kind of try to explain some of those deviations between the bearing capacity equation and Optum. So it's quite expected that in some cases you don't get the same, and in some cases you should get the same. So I've picked a number of topics. There's a lot of other topics I could have talked about, but just sort of some of the more common ones that these questions we get relate to. First of all, the bearing capacity factor and gamma, then the superposition principle, something on inclined loading. We will also talk a little bit about eccentricity, and then shape, so how to go from 2D to 3D. And so the bearing capacity equation, I think everyone knows it, is this one here. So it says it pertains to a strip footing, at least in this form, and then it can be extended, of course, but a strip footing subjected to some stress that we want to determine the ultimate magnitude of. So QU is what we want to determine. We have some surcharge as well. Width of the foundation is B. It's a cohesive frictional soil, and we express the bearing capacity as the sum of three terms related to the cohesion, the surcharge, and the unit weight. And then we have the bearing capacity factors in C and Q and in gamma that depend on the friction angle. Sometimes you see two different sort of specialized bearing capacity equations mentioned for undrained analysis, where N gamma is 0 because the friction angle is 0, and NC is your famous 2 plus pi, and C takes place is the undrained shear strength in this case, and then the drained equation where usually C is assumed 0. I will mostly refer to just the full one. And then the bearing capacity factors. So in C and in Q, there is sort of universal agreement on those. And then the first problem is, what about in gamma? Because you see different expressions of in gamma in different codes, in different textbooks, and so on. This expression here is from Eurocode 7. So, but there's someone called Brink-Hansen as well, who says it should actually be a factor of 1.5 instead of 2 here. There's Meyerhoff, which is also a common one, which says a factor of 1, but then a factor of 1.4 here in tan phi. And there's a huge number of other equations out there. And so the question is, which one should be used? So, but just to take one step back and look at how this whole thing, the bearing capacity equation, came about. It came about, I think it's fair to say, initially by first considering a weightless soil. Prandtl and Reisner came up with the exact solution actually in this case. That's where the NC and NQ come from. I believe Prandtl is behind NC, and then Reisner later determined NQ. And they found that the bearing capacity equation in this case of a weightless soil could be expressed as a sum of these two terms here related to the cohesion and the surcharge respectively. So then that's could be your first verification example of weightless soil, and I've set one up here. I've used C of 5 and a friction angle of 30 degrees, surcharge 20, no unit weight, 10,000 elements, upper and lower bounds. And I like to take the average of the upper and lower bounds. That tends to give a really good estimate of the exact solution. In this case, this average is in error by 0.2%. So really good accuracy, and solution time of 20 seconds approximately on my old laptop for the total upper and lower bounds. So that's at least some verification, which is good. Then, of course, most soils do have some unit weight, and I guess one of the idea that came up historically was that, which is quite a natural one, is that since for a weightless soil, the bearing capacity can be expressed as the sum of these two terms here, why not try to include unit weight by basically adding on another term? The gamma B here is, you can show by dimensional analysis, it has to kind of be like that. The 1/2 is a kind of a historical coincidence, and then there is the gamma, in gamma, the third bearing capacity factor, which then should be determined. So this is the superposition principle, and it can be shown that this leads to a conservative estimate of the bearing capacity, provided, and that's very important, that N gamma is exact, that it's the exact N gamma that's used. And what do I mean by the exact N gamma? Well, I mean the solution to the famous or perhaps infamous N gamma problem. So the problem where you have no cohesion and no surcharge, and where you can express the bearing capacity in terms of this equation here. If you have the bearing capacity, you can of course back calculate N gamma. And so it's kind of important to have N gamma. It's the last thing that's missing, and it's turned out that it's turned out to be a lot more challenging to determine N gamma than in C and in Q. And I've said here there's a 100-year search for the exact N gamma since the 1920s, which is, I think it's a little less than that, but a huge number of N gammas have been published and are in use in different places. This person here, Diaz Segura, in 2013, I guess, trawled through the literature and came up with 60 different N-gamma expressions. So they're all listed here, starting from Tezaki, who I believe came up with the superposition principle, 1943, and through the decades here. So that's 70 years between Tezaki and this publication of this table. So about a little less than 1 N-gamma per year. This was the state of affairs, I guess in some people's opinion, still the state of affairs, because you still see N-gammas being published. But in reality, the exact N-gamma is actually available and has been available since 2005. It was presented at this IACMA conference by Chris Martin. This is from his slides. You can download those from his webpage, and there's an accompanying paper as well that has all the details of how this exact N-gamma was determined. It was determined using the method of characteristics, so by basically calculating very accurate upper and lower bounds. These could be calculated to within an arbitrary number of digits. He did it to a large number of digits, I think 6 or so, which for practical purposes is more than enough. So these are exact solutions, even though they have somehow been computed numerically. And as he of course showed comparisons with other expressions as well. Meyerhoff, Hansen, pretty good. These are the errors for different friction angles. Vesage, pretty terrible. Eurocode 1996, but it's the same here 24 years later. Not great either, and Poulos et al, not a very well-known one, and not really too bad either. So so this exact N-gamma is actually available, and it was determined in 2005. An analytical expression is not available. That's not how the problem was solved, but that doesn't, I think, detract from the exactness of the solutions. And you can come up with various curve fits for the N-gamma, for the exact N-gamma. This one is a pretty accurate one and a simple one as well. It's actually very similar to the Meyerhoff solution. It's just a factor of 1.34 instead of 1.4. So that's really good, and that gives us then a bearing capacity equation, which is conservative, but not that much on the safe side. In order to find out exactly how much on the safe side, well, or in order to solve this problem, really, there's only really numerical analysis, so full numerical analysis in one way or another. For example, with Optum G2, and this is the same example as before, now with a unit weight of 18, upper and lower bounds, the average, 933, the bearing capacity equation, yes, it gives a conservative estimate that's expected. In this case, it underestimates the bearing capacity by 16%. So that's quite typical. Of course, it's problem dependent, but it's sort of in that range typically. So again, there's an expected deviation from the bearing capacity equation and Optum in this case. Then I wanted to say something about inclined loading. So loading where we have where the load is inclined like that, or you can think of it in a different way. You can think of it as still having a vertical load and then also a horizontal component. So you could think of determining the ultimate limit load, the ultimate vertical limit load given a certain horizontal load. And that's the way the bearing capacity equation works. It still is with respect to the vertical load, but inclination factors are now included to take into account that there is a horizontal load as well. This is the Eurocode 7 inclination factors for a strip footing. I had a look at the special case where we have a surface foundation on sand. So no cohesion and no surcharge. And we have then just this simple equation here where the I gamma according to Eurocode 7 is this expression here, 1 minus h divided by v. And I thought that was not exactly optimal, so I had a look in some other codes. The DNV guideline, it's sort of the same kind of thing. There's a 0.7 here, and then there's a factor of exponent is 5. The problem with these is, of course, that you have something called sliding as well. So, and that happens once the horizontal force is equal to the vertical force times tan phi. And you would expect the bearing capacity or the inclination factor to be 0 in this case. But these two expressions, at least for sort of normal friction angles below, let's say around 30 degrees, the inclination factor is of course not 0 when you have sliding. So you need a separate check for sliding, which sort of you'd think it should be built in. So you can try to do that, and I've tried to do that. So you want to make the factor a function of this sliding ratio. I've introduced an exponent m. It turns out to be friction angle dependent, but it's pretty accurate, actually, it turns out. Then another way of looking at it, instead of looking at inclination factors, you can convert this result basically into a VH diagram, which is a kind of a neat way of looking at things instead of just in terms of the inclination factors. So basically, you ask yourself, what combination of H and V lead to failure? And so you rearrange the equation a little bit, and you come up with something like that, and eventually you can express it in this form here. And then you can plot up your VH diagram, and that's what I've done here for 25 degrees. So, but just to show that there are issues with not really obeying the sliding limit with the conventional expressions, whereas this alternative one, the blue one, has the right sort of tangent down here at the origin, and the dots here, or the squares, are G2 calculations. That's basically what the blue curve has been calibrated to, of course. So no separate sliding check is necessary here. It's built in, and I think it would kind of be reasonable to expect that it would be built into these inclination factors. Just a few words on how to determine these VH diagrams using Optum G2 or G3 as well. So you can do it in different ways, and it's somewhat problem dependent. Exactly, is it a VH diagram or VM diagram, or what is it that you're looking at? But in this case, with a VH diagram, what you want to do is you want to first know what the limits are with respect to V. So determine the minimum V and the maximum V. So the minimum is of course 0, so that's kind of trivial. And then the maximum vertical force, that's a regular bearing capacity calculation. And then what you start doing is you have these 2 points, and then you start determining the ultimate H, the ultimate horizontal load for a fixed vertical load somewhere in between the minimum and the maximum. So you fix the vertical load and then determine the maximum horizontal load to basically get this point here. And you go along, in this case, right to left, and determine a given number of points as you please. So just to show an example. So this is basically the example that generated the points I showed before. So to determine the maximum V, regular bearing capacity analysis, or regular limit analysis, I get a load multiplier of 6, something like that. Then I go here right to left, so I apply a fixed vertical load, somewhat less than my maximum load, and then determine the maximum horizontal force. And I then can see how basically the failure mechanisms change as the load inclination increases, and I'm getting now down close to the origin where things are kind of dominated by sliding. So these VH diagrams can be, these calculations can be set up really quite quickly and processed very quickly as well. It can be done in the user interface. If it's sort of just a one-off thing, then that's what you might want to do. start with one stage and then clone, of course, and make modifications. But it is also possible, and I think that's kind of an attractive alternative if you do this on a regular basis, to access Optum G2 via MATLAB or via some sort of scripting language. Doesn't have to be MATLAB. That can be done, and there's a video I would just sort of like to say on our YouTube channel on how to access the computational core without actually having to go through the user interface. So that's is more convenient for sort of these parameter studies as well, and definitely for the generation of these VH diagrams. Eccentricity is the case, of course, where we where we don't have a central load anymore, where the load acts at some distance e from the center of the foundation. And so that's relevant for these types of structures here. For example, a relatively light structure like a chimney with a sort of a good wind, a large overturning moment, or equivalently a large eccentricity. Sometimes these eccentricities get a bit too large, so that's of course what needs to be avoided. So on the surface of it, the bearing capacity equation handles eccentricity in a very straightforward way. But when you start getting into the details of it and how to basically compare your bearing capacity equation with numerical analysis, things get somewhat tricky. So what the bearing capacity equation says we should do is that we should simply just use a different width. We should use the effective width instead of the total width. So that's B minus 2E. So we are saying there will be a tendency for this foundation to lift off, to sort of tilt. And so what we are saying is that the part of the foundation that's actually active in contact with the soil is this bit here on the right. So that's B divided by 2 minus E, and the same on the left. And so that gives an effective width like this. So what the bearing capacity equation says is that proceed as usual, but just with a foundation with a smaller width. And that thing as usual means that actually it's implicitly assumed that the surcharge, if there is any, acts all the way up to the center of this new fictitious foundation. And that's something, when you do numerical analysis, that is somewhat tricky, right? Because you can't apply this surcharge. You don't know what part of the foundation lifts off. So on the other hand, you have, the foundation has some weight, but that weight would normally be part of the vertical force. So things get a little bit messy and a little bit tricky. And we will actually have a separate webinar on this topic of foundations subjected to large eccentricities, mostly in how to handle that in 3D, and it's going to be with reference to a really interesting practical example of the design of a foundation for a tall chimney. So it's something that is a bit tricky, but to make some basic comparisons, what we could of course always do is set up a problem like this. This is on sand. I've not included any surcharge, just to at least eliminate one sort of source of you say uncertainty. And then we could place the load at some distance from the center of the foundation. We would call this the eccentricity, and then simply determine the maximum load given some eccentricity. And then we could play around with whether the foundation has any self-weight or not. So if we make things as simple as possible and assume that the foundation is weightless, well, then we have this comparison here with, well, Eurocode 7, but every code is the same, the effective width or effective area approach. This is the normalized vertical force, so V divided by V max, versus the eccentricity ratio. So 0 is central loading, 0.5 is you have the force right out at the edge of the foundation. So really, really good agreement between the code and the analysis, numerical analysis, and this is how it looks. This is for an eccentricity ratio of 0.4. So we have a really pretty significant lift off, And if you look at the forces underneath or the stresses underneath the foundation, you will see that they are complying more or less with this. Not completely, but they're in pretty good agreement with the basic assumption that the part of the foundation that is actually in touch with the soil is the part corresponding to the effective width. So you could then include some. You could then assume that the foundation, like most real foundation, actually has some weight. And I've set this weight to 20 kPa. That means when it comes to the central loading, of course, the maximum external force is a little bit less than what we had before because the weight of the foundation is already included. But it also means that things are sort of less critical for large eccentricities. We can actually, in this case, place the force right out at the edge of the foundation and still have a finite capacity. So that's how it is, so comparisons with the bearing capacity equation are sometimes a little bit tricky. And this is how it fails, and you can see now that, of course, due to the self-weight, the eccentricity is effectively a lot less than or somewhat less anyway, than 0.4, and you see that as well by the contact area. So, but as I said, we will discuss this in much more detail with reference to a practical application in a couple of weeks. I just want to cover the undrained case. So undrained, no surcharge, and that's really simple. It's again, proceed as usual. We have the 2 plus pi times SU, and then we should just multiply it by B effective to get the force instead of by the total B. And if you do that, you get something like this. So this is again the maximum, or V divided by V max versus the eccentricity ratio. The code, the bearing capacity equation, just gives us sort of a straight line. And Optum G2 gives us something different. So this is again for a weightless foundation, so it's a different effect than before. And so what I've done here is I have this problem here as well. I've basically set up the problem. This is a Tresca soil, and then run the analysis, and I get a result that looks, or a failure mechanism that looks like this, and that's kind of problematic. And what I've really missed here is, of course, the interfaces. So I've not done anything about the interfaces. At the interface, I just have the regular Tresca material, which is able to sustain tension. What I really should do is I should have, of course, a tension cutoff. So the way to do that is to basically duplicate the original soil material and then apply a tension cutoff like that. And then I like to sort of change the color as well, and then apply this material down here. If you do that, you get something really quite different. You get a mechanism that looks like this. So with a really sort of significant lift off, and also less of a capacity. And so if you sort of do things properly, you get something like that, which brings you close to what the code says you should have, and which of course is, in this case, it is quite reasonable to make this modification. So full tension at the interface versus no tension at the interface, quite a dramatic difference. Yeah, so if you look again at the stresses underneath the foundation, we do have tension unless we explicitly say that we cannot accept it. Okay, so final thing, shape. So that again is handled by, or in a similar way as inclination, by basically multiplying on shape factors, SC and SQ and S gamma, onto the 3 terms. The shape factors suggested by Eurocode 7 are listed here. And so again, it's kind of pretty simple to apply this. Where things get a little bit tricky and a little bit messy is when it comes to comparisons with Optima, numerical analysis in general. Because you will see as well that there are kind of two families of shape factors, I think is fair to say. One family or one set of shape factors that are fairly large, and then another set that are fairly small. So that's, I think, is well illustrated by the shape factor S gamma. Eurocode 7 says that it's 1 minus 0.3 times B on L. So it's independent of the friction angle, and it's always less than 1 or equal to 1. Whereas Meyerhof has a S gamma as well, which is, I think, also fairly widely used, which has exactly the opposite effect. Oh, there's a B over L missing here. So this applies to a square foundation. So anyway, it's dependent on the friction angle and is always greater than or equal to 1. So if you take a circular foundation for the purpose of shape is treated in the same way as a square foundation, so it's B and L equal to 1. Well, here you have it, the shape factor versus the friction angle, Eurocode 7 and Meyerhof. And there is a factor of 2 for sort of a, well, you have to get to a fairly large friction angle, 40 degrees or so, but you will have then a factor of 2, which is quite a bit. And also, from a more qualitative point of view, you could ask yourself, does a circular foundation have greater or smaller capacity than a strip foundation? Well, Eurocode 7 says one thing, Meyerhof says something else. So that's how it is, and the only way really to sort of get to terms with who's right, Meyerhof or Eurocode, is to do some analysis. So that those analyses can be done in Optum G2. Strip footing, of course, we actually have the analytical solution for the strip footing since we have the exact and gamma. But for the circular case, we can run axisymmetric analysis and then just take the shape factor as the ratio of the capacities in the two cases. And if we do that, we get the black curve here, which doesn't really, I don't think, settle the argument of who's right or who's wrong. It tends to be sort of more along the lines of Meyerhof, but not quite. For low friction angles, it actually dips below 1 as well, and then for higher friction angles, it sort of increases in this way here. So those are the results. And then there are people, well, you could make the argument that the Eurocode shape factor is really much too conservative. There are people who would disagree with that, though, because those people would say that when we calculate N gamma, we should calculate N gamma on the basis of the plane strain friction angle. The idea being that the bearing capacity equation was developed with reference to plane strain conditions, so N gamma and all the other factors involving the friction angle should be make use of the plane strain angle. And then when you move to situations that are not plane strain, so for example 3D, then the shape factor is meant to take two things into account, both the shape itself and also the fact that you have stress states not corresponding to plane strain. So that is the reason these people would say that the shape factor is apparently somewhat smaller than you would sort of get on the base, than you would expect on the basis of the kind of analysis I just showed. So we actually had a webinar on this topic a couple of weeks ago on our new model, the FAST model, as we call it, friction angle stress state dependency model, where we are able to operate with two friction angles, the plane angle and the triaxial angle, the triaxial compression angle. And the typical ratio between these two angles is 1.12. So the plane angle is a little bit 10-12% greater than the triaxial angle. So what we should actually do to assess the shape factor is calculate the capacity for the strip with respect to the plane strain angle. And then the question is, what about the circular foundation? Because it's not plane strain, but it's not triaxial compression either at every stress point underneath in the ground. But let's assume that it is. Let's calculate it on the basis of the triaxial compression angle. That should be conservative. And then we have the shape factor, and then this is how it looks. So this dips even below Eurocode 7. So maybe there is some sense to this value of 0.7 after all. The idea with the fast model was, of course, then that this is conservative because you're not a plane strain underneath a circular foundation, but you're not really at the triaxial compression corner at every single stress point as well. You're somewhere in between at most points, and this is where the so-called fast model comes in and takes into account that the friction angle varies quite significantly between triaxial compression, which is where it's at its lowest, and then other stress states down to extension here. So, and that seems to be the case regardless of really the density of the sand. And this ratio of about 1.1 to 1.2 seems to be where most experiments fall. So, yeah, just a brief picture of the fast model. So basically it's a more Coulomb failure surface, and then with a kind of a Drucker-Prager to cut off to basically reduce the angle here close to the triaxial compression corner. And that turns out to fit experimental data really quite well. And if you then, and here's the webinar, how to choose the right friction angle in 3D, the answer really is you should specify two angles, a plane angle and a triaxial angle. And that's possible then with this model. And if you do redo the analysis then for a final time, well, you get something that looks like this. So kind of a compromise, I guess, between Meyerhof and Eurocode 7. If you actually look at what people have determined experimentally, well, it tends to be shape factors of around 1, slightly less than 1. So I think I have quite a bit of faith in these results. So this is for the square, for a square foundation, a little bit different from a circular, but not too much. So you could make the same kind of arguments when it comes to undrained analysis. In 2D, Tresca is what is typically used, and that's fine. Then when it comes to 3D, well, there is usually a difference between the undrained shear strengths in extension and compression. We have the generalized Tresca criterion to take that into account. Again, you specify two strengths, and this is ratio extension to compression is typically around 0.7 for standard sort of isotropic clays. This is an example of some experimental data from Lade. So that is something that I think, along with the effect of the shape itself, should really be taken into account. And sometimes the codes and the different expressions for the shape factor actually do take this into account, sometimes perhaps not. But when doing numerical analysis, we have, of course, the possibility to do things, let's say, correctly from the outset. So the Tresca, the generalized Tresca model is kind of an option in the standard Tresca model that I just showed. So there's an option, standard or generalized, and you can go for the generalized, and then there's both an extension and compression SU to be specified. And that's the same in G3 as well. And that's this webinar on this undrained modeling. So conclusions, I would say in conclusion, the bearing capacity equation is pretty good actually. Sometimes it's impressively good, but there are some issues that I think would be good to have corrected. The first one is this whole business within gamma. The exact solution has actually been available now for quite a while, and it's been, I don't think there's any disagreement anymore that it is actually exact. So that would be a good idea to use. That superposition, well, it's conservative. It's well known it's conservative. You probably don't want to really do anything about that. Inclined loading, there's this issue with sliding. You could include that into your inclination factors. Eccentricity, very interesting topic that we'll talk more about in a couple of weeks. And not necessarily that straightforward to handle with the bearing capacity equation. You have to be a little bit careful, and it requires some attention to detail also when it comes to the numerical modeling. And then shape, or going from plane strain to 3D. Well, there's the whole geometric issue, but there's also, I think, reconsideration of the appropriate soil model to be made. More so the fast model, for example, instead of the more Coulomb, and the generalized Tresca, or the AUS instead of the standard Tresca. And you could look, of course, as well at a more sort of proper modeling of embedment rather than via surcharge. So the soil above the base of the foundation, of course, has some strength, right? And if you're confident about that strength, it would be natural to include that into the analysis. Some versions of the bearing capacity equation come with depth factors. I haven't talked about that, but of course, when doing numerical analysis, it's sort of straightforward to just model up the problem as it is. And there's all kinds of other well-known limitations where the bearing capacity equation doesn't really apply. Layered soils, increase of strength with depth for undrained analysis is an issue. The effects of torsion, this is something that we will be talking about in the upcoming webinar. But okay, I think this is it, and I will then have a look at whether we have some questions or any raised hands as well. If I don't know, I just need to see the list of participants.
Yeah, there are a couple of raised hands I can see, Kristian.
Okay, so hello.
Hello? Hello, can you hear me?
We can hear you, yes.
Okay, this is Puyan from COWI. So very
Puyan.
interesting, very interesting software. And actually in our company, the usage of Optum is getting higher now. But for me, you know, this is the first time that I am seeing the result of the software. I just want to know which kind of the finite element solver do you have now in Optum? Is it the implicit FEM, or do you have also explicit, something like the one that
Okay, so that's a good question. So because it's in a way neither of those two. We have a slightly different approach to basically solving the equations, and it is via optimization. So most of the results actually all of the results I showed you here have been calculated using limit analysis. So so limit analysis is an analysis type that naturally generates an optimization problem. Determine the maximum, the highest possible lower bound, the smallest possible upper bound. And it's a calculation that can be done in one quick go. So is my screen still shared? So let me
yes.
Screen, yeah. So if I was to switch to Optum and run one of these problems here, say this one here, you can see my setting is limit analysis. And I have a force here, a load here. It's a so-called multiplier load, meaning that we would like to know by one number should we multiply this load. It has a value of 1 in order to basically have this foundation fail. And so it doesn't require any load displacement analysis. It doesn't require sort of this usual simulation approach to things. It's just one quick calculation that actually then just gives you the result. And there's mesh adaptivity I can see included in this run here as well. So that's for limit analysis. It's really a really useful analysis with strength function analysis. And when it comes to deformation analysis, so load settle way, I mean, we can compute load settlement curves as well as any other finite element program, but we do solve the equations in a slightly different way. So we basically solve an optimization problem at each step along the way to generate this load displacement curve. It's something that it leads to a huge, really good robustness, and it's also pretty expedient as well. So that's how we do it.
Okay.
Yeah.
So basically, it's a one advanced method of what GeoSlope was doing. You know, the LEM analysis of the GeoSlope and the C.
Yeah,
Yeah.
I don't like to be. I mean, I know limit analysis and limit equilibrium have sort of similar names, but they are really quite different methods. And limit analysis is only part of this whole package. Regular deformation analysis, excavation, stage construction, and all the rest is very much part of the package as well. So so I think it's really quite different from GeoSlope.
Okay.
But I mean, slope stability analysis is a real strength of the program, I would say, along with many other strengths. So.
Okay, thank you.
Yeah.
Just one question. Is there any reference, any published articles or something about this methodology that I can look at it?
Yes, we can point you in the right direction if you to send us a mail. There's already quite a bit in the theory manual. So the manuals come with the program. They're available here in PDF. The examples manual, I should say, is probably the most interesting one. It has a huge collection of examples, but there is also materials model manual, of course, as well. But there is also the theory manual, which actually goes through the whole theory of
Okay.
how everything is done. So yeah.
Okay, perfect. Thank you.
No worries.
Okay, Kristian, there is a very good question here, I think.
Okay.
This guy Lee here, he asked, sorry for the silly question, but if the bearing capacity equation is pretty good, why should we use software to predict the capacity? And the simple answer, I think I can answer the first part is, well, you shouldn't, right? So if you can get through with the bearing capacity equations, you don't have to go further, then the job is done. I guess we agree on that part, Kristian?
Yes, we do, yes.
Yeah.
The problem is, I mean, this wasn't highlighted really in this webinar, but of course the bearing capacity equation has some fairly severe limitations when it comes to the kind of scenarios you can deal with.
Exactly.
But yeah, it can get you through a lot at the same time. So
yeah. So Lee, if you come across, let's say, more complex things, like it could be a foundation near a slope, foundation interaction, foundation on some layered soil on some difficult soils, then it might be, it often turns out that the bearing capacity equation is quite hard to use. Actually, you spend a lot of time on it. And in that case, using a program like Optum G2 would make things, or will make things, easier and faster.
Yeah.
Yeah.
There's a question not really related to this, but a user says that he's had some problems getting a reasonable result for a. I'm not sure really what it's about, but if that's the case, then please do get in touch. If you think that something looks funny, then just get in touch. Support at optumce.com. Can you plot the load versus displacement curve if you load incrementally a circular plate founded on sand? Yes, absolutely. I don't know if this question came after what I just showed here. So this is not sand, but this is this was an elastoplastic analysis I did here, and we can include a so-called result point. So then we will be logging the results at that point. Then I do the analysis and generate the load displacement curve. And we can then, it shows work, so that's kind of related to displacement, but it's not really a displacement. And then once the results, the analysis is done, we can go into this XY plot, select the point, plot the load versus, the load the displacement versus the load multiplier. So the displacement there on the x-axis, it's real displacements, not displacement rates, right? So that's entirely possible to do. And there are no issues, I should say, either with interfaces or anything. That's kind of like the convenience of limit analysis carries over to elastoplastic analysis. So
There are a couple of hands up, Kristian, in the in the attendee list.
Okay, let's take one here. Hello?
Hello?
Hello.
Hello?
Hi.
Hi, how are you doing?
Pretty good. How are you?
Thank you very much. Thanks for the presentation. I really liked it. My name is Payman, and actually I'm working for Fluor in Canada.
Okay.
I really enjoyed the way that you're dealing with the inclination of the loads, but my question is sometimes we have a problem with having a purely horizontal load at a certain depth without any vertical load apart from the surcharge load. And then we need to limit the deformations to elastic so that we don't let any plastic deformation to take place within the soil. Would you recommend this methodology over KPKA analysis, which is typically done for those kind of scenarios where we have pure horizontal loads? This is my first question. And the second one is about ratcheting. Because sometimes when you have loads being applied in different opposing directions, the soil might develop some ratcheting, and then you will have some plastic deformation taking place.
Sure. For the first question, limit analysis would not be the way to go, right? In that case, if you want no plasticity, because limit analysis corresponds to a fully developed plastic solution. So in that case, it would be elastoplastic analysis that you'd be looking at, and that's possible to do as well. So you should have a look at that. And for the second question with ratcheting, yeah. So that will require the modeling of a large number of unloading, reloading cycles, I'm assuming, right?
That's correct.
Yeah, and that can in principle be done. What I would be a little bit worried about, to be honest, would be that these types of ratcheting simulations, of course, are very heavily dependent on your model, right?
Correct.
I'm not sure it might be also due to pore pressure generation. But we have a fairly good, what I can say is we have a fairly good collection of models. None of those have specifically been tailored to deal with ratcheting, but I think some of them could possibly do a reasonable job. Fully coupled analysis is available as well if pore pressure generation is an issue, and specifying loading, unloading cycles, well, that can be done as well. So yeah, I would encourage you to give it a go.
That's good, because one of the problems that we are having here with a more Coulomb model is that the unloading modulus is being assumed same as the loading modulus, and that's why in this type of situation we use a hardening soil model, and convergence is usually better. We typically use Plaxis for that, and just wanted to see if you would recommend this software as an alternative to Plaxis.
Absolutely, absolutely. So we have what we call it the hardening more Coulomb model, but it's basically the same as the hardening soil model. It's exactly the same principles anyway. Then there's slight differences where we operate with an E50 and an EUR, right? So
Correct.
So that model, that's a pretty good model, I think. And if that's what you're using already, then definitely, I mean, there's no reason that you shouldn't be using Optum. So yeah.
Oh, good. Thank you.
So then, in that, yeah, no worries.
Payman?
Yes.
Hey, Jørgen here from Optum also. Just wondering, are you having problems with this? I mean, what are you doing today, and are you happy with what's going on today, or since you're asking for alternative methods?
I'm happy with actually that, but the thing is that I'm looking into, because basically I really want to have your opinion on that. Basically, those bearing capacity formulas have been developed for vertical loads and not for horizontal loads. And I was always curious as to why they never considered horizontal loads, pure horizontal loads. Because typically when it comes to horizontal loads, we go back to Ka, Kp, and passive and active earth pressures. And we don't use the bearing capacity formulas. And I still don't know why that is the case, why they never looked at that problem, same as vertical loads.
Yeah, I mean, there is, of course, I mean, inclined loading is possible to take into account, but are you talking about the case where the foundation is embedded? And
yes, the foundation is embedded, and we have, just imagine the problem that we have is for a pipeline, actually.
Sure.
No, we have.
Yeah. Then it's a kind of a, then you're in earth pressure theory, not bearing capacity theory, right? That's how it would usually thought of. In Optum, I mean, as in any other finite element program, it's a question of setting up the program and then, modeling your physics. And then, you are not going to be able to distinguish between whether it's a earth pressure problem or a bearing capacity problem. It's a mechanical problem, right? So
that's correct. This is exactly how things are. But just out of my curiosity, why they didn't consider this scenario in bearing capacity method? Why did they go to passive active theories in the first place?
Yeah, I think, I mean, it's probably too much it would probably be too difficult, right? So there's already enough difficulties as it is. And so I would think it's a question of the fact that you would be extending the sort of the scope of the kind of problems you would consider very, very substantially. So I think it would probably be too much.
Okay, thank you.
Should we have one last question, Kristian? It's we're getting close to the end.
Yes. So there's a question on tension cutoffs for undrained soils.
Yeah.
So what are my thoughts on applying tension cutoffs for undrained soils? Well, I mean, I would say that unless you have some kind of good reason not to apply it, unless you have the soil for one reason or another stick to the structure, then I would think that a tension cutoff would always be the way to go. And that, of course, is going to decrease your capacity compared to the case where you have no tension cutoff. So you're welcome to get in touch with that if that's something you want to discuss further. But that would be my.
Can you just sum up that? Can you sum up that, Kristian?
Yeah, I would say unless you have some sort of good reason not to apply tension cutoff, then I would think you would apply it by default.
Yeah.
So in this case, for example, why would the foundation stick to the soil? I can't see any good reason why that would happen. So a tension cutoff would be the way to go, I would say.
Yeah.
But there can be things where, due to under pressure and things like that, you could have effectively some sort of adhesion. So then you wouldn't apply it.
Great. All right. I think that is then the end of today's webinar. Thanks everyone for joining in, and be sure to come back next Thursday for Bertrand Maillot from GEC and hear about limit analysis for tectonic plates and stuff, and how they use Optum for this. This is going to be really, really amazing, and we're looking forward to it anyway. So have a great today it's a day off, I think, in many parts of the world. So if you have the day off tomorrow, then have a great weekend. If not, have a great day at work, and see you again next week.
Yeah, see you.
See you.
See you.